Huygens principle. So Huygens' first principle states that each point of the wavelength is the source of secondary disturbance called secondary wavelets, which travels in all directions with the speed of light in the medium. That means each point of the wavelength, is the source of secondary disturbance called secondary wavelets. Which transmit in all directions with velocity of light. In the medium. Each point of the wavelength is the source of secondary disturbance called secondary wavelets, which travels in all directions with the velocity of light in the medium. That means let us consider a point source like this, which emits light in all directions. Suppose we join the locus of all the points, we will get spherical wavefront like this. So this is the primary wavefront. This one is the primary wavefront. By joining the locus of all the points, we will get wavefront that is called as primary wavefront. Okay. So here, each point of the wavefront, so the points of wavefront. So each point of the wavefront is the source. These points are itself act as a source. Each point of the wavefront is the source of secondary disturbance and called secondary wavelets. That means each point itself emits small waves. This wavelets means small waves. Each point of the wavefront emits secondary waves, that is small waves. Each point emits small waves that is called as secondary disturbance. Like this. So each point emits small waves. That small waves is known as secondary wavelets. The small wavelet. What is the source of the secondary wavelets? So each point on the primary wavefront is the source of secondary wavelets. So each point on the wavefront is the source of secondary disturbance called secondary wavelets. These secondary wavelets travels in all directions. The secondary wavelets travels in all directions with the velocity of light in the medium. So this is the first principle. Once again I will repeat. Each point on the wavefront is the source of secondary disturbance called secondary wavelets, that are called as secondary wavelets. Okay, that transfers in all directions with the velocity of light in the medium. Okay. Huygens' second principle. So Huygens' second principle states that the surface drawn tangentially to the secondary wavelets in the forward direction gives a new wavefront called secondary wavefront. So Huygens' second principle states that the surface drawn tangentially to the secondary wavelets in the forward direction The surface drawn tangentially to the secondary wavelets in the forward direction gives a new wavefront called secondary wavefront. Don't confuse this wavelets with wavefront. Wavelets means small waves. Wavefront means locus of all the points which oscillates in the same phase. So the surface drawn tangentially to the secondary wavelets. So these are the secondary wavelets. Where you have to draw the tangent line? So here or here, the surface drawn tangentially to the secondary wavelets in forward direction. That means we draw this tangent in the forward direction. Not here, we draw the surface tangential line in the forward direction because energy of light is transmitted in the forward direction. It does not transfer in the backward direction. Okay. So the surface drawn tangentially like this. Tangential line. This is the tangential line. The surface drawn tangentially to the secondary wavelets in the forward direction gives a new wavefront. That wavefront is called secondary wavefront. That wavefront is called secondary wavefront. Okay. That is the Huygens second principle. The surface drawn tangentially to the secondary wavelets in the forward direction gives a new wavefront called secondary wavefront. Okay. So this is our primary wavefront. So secondary wavelets are obtained from the primary wavefront. So tangent line drawn to the secondary wavelets. Sorry, this is secondary. Secondary. The tangent drawn to the secondary wavelets gives a new wavefront, that is secondary wavefront. I think it is clear to you now. Derive Snell's law using Huygens principle. We know that Snell's law states the ratio of sine of angle of incidence to the sine of angle of refraction is equal to the refractive index. Now we can prove this Snell's law by using Huygens principle. Okay. For that, let's draw an interface, that is a surface. Let us call this surface as P dash. When a plane wavefront is incident on this surface, what happens? It gets refracted or reflected. Now, when a plane wavefront is incident like this is a plane wavefront. This is the plane parallel beam. When parallel beam of light incident on this surface, what happens? The left edge of the parallel beam incident on the surface first than the right edge. Okay. So plane parallel beam means there are some here in between the gap, some rays or parallel rays are present. Okay. When first left ray reaches the first the interface, what happens? Here this is the first medium and this one is the second medium. So here we consider the first medium as rarer medium and second medium as denser medium. Okay. So velocity of first medium can be taken as V1, velocity of second medium can be taken as V2. Okay. So refractive index of first medium can be taken as N1, refractive index of second medium can be taken as N2. Okay. When parallel beam of light incident at the interface first, what happens? It first reaches the interface. Suppose if we draw a normal here, so this is the angle between incident ray and normal. What is that angle? That is the angle of incident I. When ray reaches the interface, what happens? It gets refracted here. So here the ray of light travels from rarer to denser medium. As the ray of light travels from rarer to denser medium, its velocity goes and decreases. As a result of this, the refracted ray bends towards the normal. So this is the refracted ray that bends towards the normal like this. Okay. So the angle between this normal and refracted ray is known as angle of refraction. Okay. But here we prove the Snell's law by using wave nature of light. In wave nature of light, we use wavefront instead of beam of light. Instead of beam of light, we use the wavefront. Instead of incident ray and refracted ray, we use incident wavefront and refracted wavefront. Okay. When at the time of reaching the interface by the first ray, the second ray is at somewhere here like this. So second ray is at the time here because the first ray reaching first and the left edge of the ray reaching first and the right edge of the ray reaching lastly. Okay. So here first ray reaching at the interface here at the certain time t. So then at that time the second ray is at present at this point. Okay. So after a certain interval of time, or at time tau, at a certain time is say 10 seconds or 5 seconds or 15 seconds, and after a certain interval of time, the first ray travels in the second medium. The first after time tau, say tau, the first ray travels in the second medium. First ray is not first ray. The left edge of the beam travels in the second medium, and right edge of the ray still travel in the first medium. Okay, so at certain interval of time, say 10 seconds, the first ray travels at a certain distance like this at the second medium. So the first ray is traveling still in the first medium with the velocity v1. It travels in the second medium with velocity v2. We know that when a ray of light travels from the rarer to denser medium, its velocity goes on decreases. So here v1 is greater than v2. Velocity of rarer medium is greater than velocity of light in the rarer medium is greater than velocity of light in the denser medium. At the same time tau, the right edge of the ray moves faster than the left edge of the ray because here the left edge of the ray travels in the second medium, so its velocity goes on decreases in the second medium. So for the same interval of time, the right edge of the ray travels faster than the left edge. So this left edge of the ray travels a shorter distance than this right edge. It is very important from the point of view of exam. Okay. So this is the distance traveled by the left edge of the ray in the second medium, and this is the distance traveled by the right edge of the ray in the first medium. They are travels in the same interval of time of this. These two rays are travels in the same interval of time. Let us call this point as C. So let us call this point as E. Okay. So according to Huygens principle, let us consider this as plane wavefront. Okay. So according to Huygens principle, each point on the wavefront is the source of secondary wavelets. So here each point on the wavefront is the source of secondary wavelength like this. So secondary wavelets like this. So each point forms the secondary wavefront like this. That means they form small waves. Wavefront means small wave. So this point forms a disturbance and forms a wavelets. This forms wavelets. So like this forms a wavelets. Okay. So this is the first principle. Huygens first principle. What is that Huygens first principle? Each point on the wavefront is the source of secondary wavelets. Okay. This is known as secondary disturbance called secondary wavelets. So this is secondary wavelets. According to Huygens second principle, the surface drawn tangentially to the wavelets, gives a new wavefront called secondary wavefront. Suppose if we draw a tangent for this, we will get a new wavefront. Okay, this is secondary wavelength. In here, this is the refracted wavefront. That is CE is the refracted wavefront. Here, AB is the incident wavefront and CE is the refracted wavefront. So the distance BC and AE are travelled in the same interval of time t, but BC not equal to AE, or BC is greater than AE because BC is the first medium and AE is in the medium. Okay. Here AB is the incident ray, C is the refracted ray, and I is the angle of incidence, R is the angle of refraction. Okay. So this is not necessary because I draw this for your convenience only. Okay. So let's draw an interface. That you call this interface as P dash. Okay. While a parallel beam of light incident here, this is the parallel beam of light that is incident here, like this. Okay. So let's draw a normal here. So the angle between the normal and incident ray is known as angle of incident. Okay. So now we draw the incident wavefront. So at certain interval of time t, the left edge of the ray reaches first than the right edge. So at this time, the right edge of the ray is still here. At the point, at certain point, say that point as, at certain time t, when reaching the point, when left edge of the ray reaching the surface, the right edge of the ray is at certain point. Let us call that point as B. Okay. So this is our incident wavefront. That is AB is the incident wavefront. In the ray optics, we use beam of light, but in wave optics, we use incident wavefront, refracted wavefront, like that. So here AB is our incident wavefront. Okay. At certain interval of time t, at a certain interval of time tau. So this first edge of the ray moves in the second medium. That is, in the second medium, velocity goes on, decreases. As a result of this ray gets bends towards the normal. This ray gets bends towards the normal. So this is our refracted ray. So the angle between refracted ray and normal is known as angle of refraction, that you called as R. Okay. So this is the angle of refraction. So at certain time tau, at the same interval of time tau, the right edge of the ray travels a distance BC and left edge of the ray travels at a distance, say, AE. For our convenience, we can draw only now. It is not necessary to draw spherical wavelettes. We draw only semicircular arc like this. Okay. Left edge of the ray travels at a distance AE. Okay. Now we draw a tangent for this like this. So here CE is the refracted wavefront. C is the refracted wavefront. AB is the incident wavefront. C is the refracted wavefront. We call this point as E. C is the refracted wavefront. Okay. This is the angle of incidence, angle of refraction. For here, this is the angle of incidence and this is the angle of refraction. Okay. From the figure, AB is the incident wavefront, C is the refracted wavefront. Students, please notice that BC is always greater than AE because velocity in the first medium is greater than second medium. In the first medium, we shall take rarer medium and in second medium we take denser. Okay. So this is our first medium and this one is the second medium. So refractive index of first medium can be taken as M1, refractive index of second medium can be taken as M2, velocity of first medium can be taken as V1, velocity of second medium can be taken as V2. Okay. So from the figure, P dash, what is P dash? Interface. Okay. AB is incident wavefront. AB is the incident wavefront. Okay. Next, CE is the refracted wavefront. CE is the refracted wavefront. CE is the refracted wavefront. C is the refracted wavefront. Okay. N1 is the refractive, RI means refractive index. So refractive index of first medium. N2 is the refractive index of second medium. Okay. Next V1 is the velocity of light. Velocity of light in first medium. V2 is the velocity of light. Velocity of light in second medium. It is this velocity of light in second medium. So this is 90 degree, that is perpendicular. Okay. So the distance BC and AE. The distances BC and AE are travelled. BC and AE are travelled in the same time. Say tau. In the same time. Say the time as tau. The time taken to travel the distance BC and AE are same, that is tau. So distance travelled BC is given by V1 into tau. Because velocity is the distance travelled by time taken. Velocity is nothing but distance by time. Here BC is the distance in the first medium. So V can be taken as V1. So distance is BC by time tau. BC by tau. So V1 is equal to BC by tau. So BC is equal to, which implies BC is equal to V1 into tau. Similarly, V2, velocity in the second medium. Velocity is nothing but distance travelled by time in the second medium. V2 is equal to distance travelled is AE by time tau. Because the time interval is same between BC and AE. Okay. So if V2 is equal to AE by tau, then AE is equal to V2 into tau. Okay. Next, from the right angle triangle ABC, here we have two right angle triangle, that is ABC and ACE. First, from the right angle triangle from right angle triangle ABC, sin I is equal to, the angle is I, so sin I is equal to, what is sin theta? Opposite by hypotenuse. Here theta is I, therefore sin I is equal to, opposite side is BC and hypotenuse side is AC. So sin I is equal to BC by AC. Okay, sin I is equal to BC by AC. Similarly, from the right angle triangle ACE, from the right angle triangle ACE, here theta is R, so sin R is equal to, opposite by hypotenuse. Here opposite side is AE and hypotenuse side is C. So sin R is equal to AE by CE. Sin R is equal to AE by AC. Okay. So next, divide this by this, that is sin I by sin R is equal to, what is sin I? BC by AC, that divided by, what is sin R? AE by AC. So AC get cancelled, remaining sin I by sin R is equal to BC by AE. But we know the expression for BC. What is BC? BC is given tau. Substitute BC instead of BC. B1 tau will get sin I by sin R is equal to, BC V1 tau that divided by AE can be written as V2 tau. The tau will cancel. Remaining sin A by sin R is equal to V1 by V2. Sin A by sin R is equal to V1 by V2. That is sine of angle of incidence to the sine of angle of refraction is equal to ratio of velocity of light first medium to the second medium. But we know the relation between velocity and refractive index. What is that? V1 by V2 is equal to N2 by N1. V1 by V2 is equal to N2 by N1. So this equation becomes sin A by sin R is equal to V1 by V2 can be written as N2 by N1. Sin A by sin R is equal to N2 by N1. So this can be written as N1 sin A is equal to N2 sin R. This is the Snell's law. N1 sin A is equal to N2 sin R. This can also be written as N2 by N1 can also be written as N2 1. So the ratio of sine of angle of incidence to the sine of angle of refraction is equal to refractive index. This is the Snell's law. Okay. Now we derive the Snell's law by using this Huygens principle. This is very important at the point of board exam. If lambda 1 is the distance travelled in first medium, suppose if lambda 1 is the distance travelled in first medium and lambda 2 is the distance travelled in second medium. Lambda 2 is the distance travelled in the second medium. Then lambda 1 by lambda 2 becomes distance travelled by first medium to the distance travelled by second medium is given by, what is the distance travelled in first medium? That is PC. Distance travelled in the second medium is AE. So lambda 1 by lambda 2 is equal to BC by AE. That will be equal to, what is BC? Here BC is AE. What is AE? AE is V2 tau. So V tau will cancel. Then lambda 1 by lambda 2 is equal to V1 by V2. Or lambda 1 by V1 is equal to lambda 2 by V2. Lambda 1 by V1 is equal to lambda 2 by V2. This is the relation between wavelength and velocity. When light travels from rarer medium to denser medium, its velocity goes on decrease. This proves that when the light travels from rarer medium to denser medium, its velocity goes on decreases, but frequency remains same. Frequency remains same.